Today we're going to start to discuss how we can actually graph the functions of sine theta and cosine theta on a regular Cartesian XY coordinate system. Now when we think about a function, we're always graphing inputs versus outputs. So something you plug in for x causes some output in terms of y. So for our trigonometric functions, the way we're going to plot this is we're going to say that the y value is equal to sine of some x value. And so now we just have to recognize that the x coordinate here is our input and our y coordinate is of course our output. But when we think about this in terms of the unit circle, keep in mind that the sine of each angle is giving me some sort of ratio. So the sine of pi over 6 is 1/2. Sine of root 2 over 2, sine of pi over 4 is root 2 over 2. Sine of 2 pi over 3 is root 3 over 2. And so we're seeing that certain angles will yield certain ratios. So in this particular case, what we've got to recognize is that our input is going to be our angle, while the corresponding output is going to be our ratio. So when we think about this on an x and y graph, we need to think that our x-axis is describing all of our angles, while the y outputs are corresponding to each of the corresponding ratios. So let's think about how this would look on a graph. Well, since we're plotting each of our angles corresponding to each of our indicated ratios for sine, if we wanted to graph y equals sine x, then we would start off by recognizing that at the angle of 0, the y coordinate, which stands for sine x, or sine of theta, is 0. So that means at the angle of 0, we're going to plot 0. So now if we were to continue to look around here, we'd recognize that as I start to move from the angle of 0 to pi over 6 to pi over 4 to pi over 3 to pi over 2, look at how all my y values start to get larger and larger. So that means that if we were going to go for each of these quadrants, I would go through a certain amount of ratios up to till pi over 2, certain ratios until I get to pi, certain ratios until I get to 3 pi over 2, and then certain ratios until I get to 2 pi. And then by the time I get to 2 pi, the pattern starts over again. So I know that by the time I get to 2 pi, my ratio is also going to be 0 because 0 and 2 pi are going to be coterminal angles. So therefore at 2 pi, our ratio is also 0. But we should also notice something else as well. By the time we get around 2 pi, we should see that the y value is also 0. So it looks like it rises from 0 up to a y value of 1 and back down to a y value of 0. Which also means by the time I get halfway between 0 and 2 pi, which is at pi, I know that my ratio is also going to be 0. So now let's look at what's going to happen by the time the ratios, or I'm sorry, the angles are at pi over 2, which is halfway between 0 and pi, and at 3 pi over 2, which is halfway between pi and 2 pi. Now, whenever we graph any trigonometric function, we're always going to be putting 5 spots on our x-axis, because these are going to be 5 of the most important components of this function. So the next thing we're going to recognize is that the y values can rise up from 0 all the way to 1, which we should recognize in our first quadrant here, based on the fact that by the time I get to the angle of pi over 2, my y value is up at 1. So at pi over 2, we plot a y value of 1. And what we should recognize in that first quadrant as well is that when I look at each of, and I don't need to necessarily draw these all the time, but I'm going to do it anyway just so we could see where they are. Let's just take a look at pi over 4. And pi over 6 is just below that. And pi over 3 is just above pi over 4. And so if I was to look at those points, then what I could see is that at pi over 6, my y value is 1/2. So 1/2 is halfway, obviously, between 0 and 1. So my y value is 1/2. And if I go to pi over 4, my y value is √2/2. Now that's a 0.71 is the approximation. So if this is 0.75, halfway between, then it's going to be a little bit lower. So I can see that by the time I get to pi over 4, my y coordinate is √2/2. And then my value at pi over 3 is going to be 0.87, √3/2. So when I plot that point to pi over 3, I end up getting a value of √3/2. And so hopefully you are recognizing that the y values are increasing in the first quadrant. And just to make this a little bit nicer, it actually reaches a high point at pi over 2. And it starts at the y or the x-axis. Well, now we're not going to be plotting all of these intermediate points here. We're just going to be looking at the locations on this graph where the graph touches 0 or where the graph reaches a maximum or a minimum. Okay, and so now let's take a look into the second quadrant. The second quadrant goes from pi over 2 to pi. So since pi over 2 to pi is just taking us back down again, we can see that all of our y values are decreasing back through those same exact ratios until I get to the angle of pi, which means that my y value should be continuing to fall until we get to pi. So we could already see, based on the values of my angles, as my angles increase, my y values get larger, but then they get smaller. So now if we were to go down into the third quadrant here, we should see that the y values continue to get smaller. But now we should realize that the y coordinates are dropping into the negative ratios, which is why each of those values are going to get down to a lowest value of -1. So that means if 1 was up above, then -1 is down below. And so by the time I get to 3 pi over 2, my ratio is down at -1. So as we continue to drop, those values get smaller and smaller and smaller and smaller until they get down to the y coordinate of -1. At which point you should see that those y values start to get larger again, from -√3/2 to -√2/2 to -1/2 until it gets back to 0. So it's traveling through the same y values on the way down as it traveled on the way back up, which is why we should see on our graph that it continues to rise again until it gets to 2 pi, at which point what we've done is we've drawn one period. A period is just one full cycle that we take from the starting point to the ending point. This is one period of the function y equals sine x. Now we should realize that if we were to go back into the negative angles, this would just continue back this way. And it would just continue in that fashion. And if we were to continue past 2 pi, it would do the same thing. It would rise up and then continue to fall. So what we should recognize with our graph is that if we were to look at y equals sine x, and what I've done here is I've drawn it just on the interval from negative, well, it looks like -5 pi over 2 to +5 pi over 2. We're going to look just at this piece right here that starts at the origin, and sure enough, we get that piece of the graph. So in general, we're going to graph one period, but we could obviously graph more than that if we wanted to. So we're going to look at how changing this function can cause different situations, or how we can cause this graph to transform. So you may remember that when you have a function where you are multiplying by a single scalar constant, let's say you had y equals x squared, and then I wanted to graph 2x squared. Well, what that did is that it multiplied each of the original sine x values by 2. So when I had an answer of 0, multiplying by 2 kept it 0. But if I multiply a y coordinate by 1 by 2, then that's going to stretch up to 2. While multiplying a y value by negative y value by 2, negative 1 times 2 stretches it down to negative 2. So you can see that by multiplying by a particular number, that's going to change what we refer to as the amplitude of this graph. The amplitude is how high it goes from the middle of the graph, from what we refer to as the midline. In this case, the midline is the x-axis, and so multiplying by 2 caused it to rise by 2 values and to fall by 2 values. Now, similarly, if you think back to transformations of other functions, if I multiply a function by a negative, then that should reflect the graph over the x-axis, because each of the values that used to be at 2, if I multiply it by a negative, comes down to negative 2. And if you're already at a y value of negative 2 and you multiply by a negative, it flips up to positive 2, which is why I now see that y equals negative 2 sine x is going to be our reflected graph. So now if we take a look at the original sine of x graph as this dotted graph, I can see that the blue graph, the stretched function, and the green graph, the reflected function, are simply transformations of the same function, but we know that the shape itself is going to be the same. Now I'd like to take a look at what ends up happening if I multiply the angle by 2. So let's think about what's happening now. If sine of an angle gives me a certain ratio, so sine of x gives me a certain ratio. But what happens when I now multiply x by a constant? If I multiply x by a constant, notice that it's not going to be raising the graph at all, because I'm still calculating sine of an angle. The biggest that sine of an angle could ever be is 1. And the smallest it could be is negative 1. So by multiplying the angle by 2, we should realize something different happened. Notice that that graph ended up smashing horizontally. We can see that what used to give me an answer of 1 is going to occur halfway between the y-axis and that value. What used to give me a value of negative 1, which was 3 pi over 2, is going to be half of that, which is 3 pi over 4. Which would imply that if I were to multiply the angle by 1/2, I would have to double the angle to get those same ratios. So look at how now it's stretched it out. And so changing the value in front of sine x is going to change the amplitude, while changing the value or multiplying the angle by a number is going to change it horizontally in terms of stretching it or compressing it horizontally. Looking at this function here, even though we know that this graph will extend infinitely in both directions, simply because I can plug in any angle I choose to for x, and I'm going to get some ratio. It may be some large angle that was from 50 different rotations, but I'm still going to get some function that's going to be periodic. So the first thing to recognize is, what does the shape look like? So because it says that it's a sine function, we've just seen that it's going to start at the origin, and it's going to increase, then decrease, then increase again. And it's going to stop where it started. But another thing to recognize, because of the fact that it is a reflection over the x-axis, is that we should also recognize that instead of starting by going upwards, it's going to start by reflecting and therefore go downwards first. So the nice thing about what we can do first is just see the basic shape. We call that the parent function. But then we want to take a look at what this coefficient represents. Okay. We refer to that as oftentimes as A. Okay. So this value right here is A. And A represents the amplitude of this function. So the amplitude is always going to be positive. So the amplitude is nothing more than just the absolute value of -2. And so the amplitude is 2. And what that means is that from the midline, assuming that this graph hasn't shifted up or down any, I know that it's going to be going up 2 units to 2. but it's also going to be going down 2 units to -2. But now there's actually 2 different methods that we could apply in order to determine what this graph looks like. You might remember from Desmos that we saw that anytime there was a multiple of the angle, that caused the graph to either stretch or compress horizontally. So when normally the single or the standard trig function would normally start at 0, end at the y value of 0, halfway between at pi, it would hit the value here, and then it would end up going upwards first and downwards second. And so this right here is basically the structure of my original graph, where the period would be 2 pi. But because of the fact that this here, which is referred to as b, okay, the coefficient of x is referred to as b, now we're recognizing that that's going to cause that period to not go from 0 to 2 pi, and it's going to start from 0 and go to somewhere else now. So there's 2 methods to determine this, and the first method is to physically find out what that period is, okay? So the period could be found by recognizing that that quantity of 3 is saying that if I take the original period of 2 pi, which is the standard period for sine of x, if I start at 2 pi, this value of 3 means that I'm going to be able to fit 3 cycles from 0 to 2 pi. So what b really represents here is the number of cycles from 0 to 2 pi. Which means if I know that there's 3 cycles that are going to occur from 0 to 2 pi, and then one last one here, then that means that I need to figure out how long is one period or one cycle. So what we're going to do is take 1/3 of 2 pi. Another way to think about it in terms of a formula is that we could really just take 2 pi, divide it by b, and therefore the period is 2 pi over 3. So instead of extending from 0 to 2 pi, we know that it's now going to extend from 0 to 2 pi over 3. And now that we know the beginning of the period and the end of the period, our job now is to just do a little arithmetic to find out what the middle point or what the midpoints are going to be. So the way that we could do this, it's relatively straightforward if you're starting at 0, because really I'm just cutting 2 pi over 3 in half to get this value in the middle. Half of 2 pi over 3 is obviously 1 pi over 3. If I now take half of 2 pi, or half of pi over 3, 1/2 of pi over 3 is pi over 6. So I know that this is going to be pi over 6, and that's where one of the max or min points is going to be. And now I want to find the midpoint between pi over 3 and 2 pi over 3. Again, there's a couple of ways to do this. We could think about this in terms of our unit circle. Recognize that pi over 3 is this green line. 2 pi over 3 is this green line. So the midpoint will be right in the middle, which is pi over 2. Or if we do it using arithmetic, we could think of it as the average between pi over 3 and 2 pi over 3. So I would take pi over 3 plus 2 pi over 3. And whatever I get, I divide it by 2. So I'm taking the average. So pi over 3 plus 2 pi over 3 is pi. So I know that the midpoint is now going to be pi over 2. Another way you could do it is just realize that if I already know that this distance right here is 1 pi over 6, and now this is 3 of those values, then I could just multiply pi over 6 times 3, which still gives me pi over 2. And so now you can see that even though the standard period at this point would have now been much wider because it would have ended at, say, 2 pi, now I can see that one period is only extending from 0 to 2 pi over 3, And so we're going to graph every graph the same. The only difference is the scaling on our x-axis. So where do we put our actual values? So this is where we can now start our graph. We know that because it's going to start at the origin, looking at the original graph we had here, it's going to end at the final part. Halfway in between is going to be here. But because it starts by going downwards, that means the first thing it's going to hit is a minimum. And then it will hit a maximum, which is why I know that it's not going to go upwards. I know that because it's a negative 2 sine 3x, I need to put my first point at the midpoint of 0 and pi over 3, and my maximum point at the midpoint of pi over 3 and 2 pi over 3. And therefore, connect the dots, and this is our graph. We need to make sure that we are curving to get to the top. Crazy there, but notice that it starts by going down to the minimum, it increases to a maximum, and then comes back down to 0. So that's one method. Now, the only difference in the second method that you could actually do is not in finding the amplitude. The amplitude is still going to be the same. It's still going to go up to 2. And so I know that the amplitude goes up to 2 and down to negative 2. Okay. But now what's going to happen is that we're going to use a different method in order to find this, find what the period is. So the way that we're going to do this is we're going to say normally my x coordinates in general, or I should say that theta in general, is going to be somewhere in between 0 and 2 pi. So since this right here is the angle theta, we know that the value of that angle has to be somewhere between 0 and 2 pi. Well, now the angle is 3x. So since the angle is 3x, that means that we're going to be able to say that 3x has to be somewhere between 0 and 2 pi. And now in order to solve for what the x coordinates are, I divide by 3, and we find out that x is somewhere between 0 divided by 3, which is 0, and 2 pi over 3, which you should notice is the exact same thing as I found in my method 1. It's just a different way of approaching the problem. I could either use the formula to find the period of 2 pi over b, or I could just find out what the interval is going to be in the first place and graph it again. So if I were to now plot 0 and 2 pi over 3 here, the method of finding the intermediate values is exactly the same. We're always going to be finding the midpoint, which is pi over 3. The midpoint between 0 and pi over 3 is pi over 6. The midpoint between pi over 3 and 2 pi over 3 is pi over 2. And once we have that, we can now start to plot our points and graph. So it turns out to be the exact same graph that we would have had before in the other method. So let's take a look at how cosine looks. So if we refer back again to the unit circle, we should keep in mind again that the x values describe cosine of that angle. So you give me a certain angle, and now what I'm going to be plotting when I graph the function y equals sine of x, cosine of x, I'm still thinking of this in a very similar fashion. I still realize that the x coordinate is the angle, but the y coordinate is, again, the ratio. But the way that we could find the ratio is by realizing that it's the x values. So now we're going to start by looking at the x values and realize that if we were to try to graph this again, now we're going to realize that the first x value at the angle of 0 is 1. So instead of plotting at the angle of 0 the origin point, I'm now going to be plotting 1 unit up the y-axis. When you look at your x and y axis, keep in mind that x is still representing the angle, which means that the angle of 0 radians, my y coordinate, or I'm sorry, my x coordinate is 1, which is really representing the output of the function value. So keep in mind that the outputs are in fact the x coordinates on our unit circle because those describe cosine of the angle. So when we plot at the angle of 0, the answer is 1, or the ratio is 1. That's going to be our first value on our graph. Now you should start recognizing as you start to move in the first quadrant here that the x values are getting smaller and smaller. Now that should make sense because if I was to start to move around the outside of this circle, notice how the x value here is getting smaller as I continue to move around the circle. So each of those values is getting smaller until it reaches at pi over 2, a y value, or a ratio of 0. So at the angle of pi over 2, my ratio is 0. Now for now to continue the angles, as I move from pi over 2, where I'm at the ratio of 0, now I start to realize that as the angle continues to increase, moving around the unit circle here, as that angle starts to increase, those values start to get smaller. And they keep getting smaller in the negative direction. So that by the time I get to an angle of pi, my ratio is now -1. So keeping in mind now, when I take a look at pi, pi is the same distance away as 0 is from pi over 2. And so at pi, I'm going to plot my ratio of -1. Now you may think, well, it looks like this is now just going to be some sort of line. But notice that just like sine of x ended up curving because of the fact that these were changing at different rates as we were moving around the circle, I should now realize that as I continue to increase the angle from pi to 3 pi over 2, my x values continue to get larger again now. Which makes sense because now we should see that as I was moving backwards at this angle, this was our x coordinate, then this was our x coordinate, and so on, getting back to 1. But then now as I'm in the third quadrant, I'm moving back again, back towards an x coordinate of 0. Which is why now, as I move to 3 pi over 2, my ratio is now back to 0. But notice that 0 and 2 pi are coterminal to each other. So 0 and 2 pi should have the same exact output, which makes sense if you look at how the x values continue to increase until it gets back to 1. So by the time I get to 2 pi, which again is the same distance away from 3 pi over 2 as 0 is from pi over 2, I can now plot my output of 1. And so if we were to now connect the dots, we should realize that it actually looks very similar to our graph of y equals sine of x. The only difference, if I were to continue this downwards, okay, is that would actually occur back here at negative pi over 2. So we should see the cosine of x, in fact, is exactly the same as the sine function, just shifted over. So cosine of x is exactly the same as the sine function shifted to the left pi over 2, which is how we represent transformations if I were to look at horizontal shifts. And so that makes sense as well, simply because sine and cosine are are co-functions, and therefore off by 90 degrees, which makes sense that cosine of 0 should be equal to sine of 90 degrees, or sine of pi over 2. So now in general, we see that sine of x is going to start at the top, decrease to a minimum, and then reflect itself curving right back up to the top, which is slightly different from the sine function. And this is how we're going to be plotting one period for cosine of x. We're now going to start looking at a different type of transformation. So the first type of transformation that we looked at was were stretches and shrinks, or stretches and compressions, where I could literally pull the graph upwards and downwards, or I could smash it inwards or pull it outwards horizontally. But let's keep in mind that one of the first things that we learned, or first transformations we learned in algebra, were horizontal shifts and vertical shifts. So I'm going to revisit just f of x equals x squared. Keep in mind, if x is ever being affected, then like this x plus 3 before it's being squared, this x plus 3 is causing the graph to shift left or right. Now, mainly it's going to be showing that whatever we plug in for x to cause this to be 0 is where it's moving. So when I take -3 and plug it into this function, I get an answer of 0. So I know that x plus 3 quantity squared shifts left 3 units. Now, if I was to look at how this one here is different, anytime I'm taking my x squared values, which are the original black values on my graph here, now I'm going to subtract 1 from each of those y coordinates. So once I ended up getting the value of x squared, subtract 1, and that causes the graph to move down. So if we were to put both of those together into one, if I ever see a horizontal shift and a vertical shift at the same time, that means that we're going to shift left and down, which is why this is the final result. So what if we were to look at something similar to this as a cosine function? Now remember why this is the graph of cosine x. Keep in mind the cosine of x at the angle of 0 starts up at 1, and it continues until it ends up getting to the top again, or the maximum, by the time it gets to 2 pi. We just happen to be plotting more periods than just one single period to see what ends up happening. So now I'd like to pick up that graph and shift it left pi over 3. Well, here's pi over 2, negative pi over 2. So negative pi over 3 would be somewhere about right here. So that means that the value that was at the angle of 0 is no longer going to be here anymore. It's going to shift to the left, which is why not only did this point here shift to the left, but every single one of our special points shifted to the left. The value that was at 0 is now pi over 3 to the left. The value that was at the minimum is pi over 3 to the left. And so what if we were to now look at this in terms of a vertical shift, cosine of x minus 1? Sometimes this could also be written as -1 plus cosine x. It means the same thing. But cosine x minus 1. That's just going to take every one of the original black points and move them 1 unit down. So where it used to be at y equals 1, now it's going to be at y equals 0. Where it used to be at y equals 0, it's going to be at y equals -1. Where it used to be at y equals -1, it's now going to be at y equals -2. So now, if I were to shift that down, this is the graph of cosine of x minus 1. So we'd like to put this together to be able to plot cosine of x plus 3 minus 1. And so when we put all of that together, notice how this point shifted left and down, giving me the indicated purple graph. We want to now be able to graph this by hand. And the way that we're going to do that is still by finding those 5 important points, the 2 maximums, the 1 minimum, and the 2 zeros. So let's go ahead and take a look at that. Now, the first thing I like to always do is find the important x-axis values that are going to show me where the maxes, mins, and zeros are. So the first thing to do is to recognize that this here is theta. Now what we could do is graph our original values of 0, 2 pi, pi, and so on, graphing pi over 2, and then shift every one of those points pi over 3. Or in other words, subtract pi over 3 from every one of those. What I like to do instead was the method I showed above as method 2, is to recognize that if theta is typically somewhere between 0 and 2 pi, or sine x or cosine x, now notice that the theta is x plus pi over 3. And so notice that now we're saying that x plus pi over 3 needs to be somewhere between 0 and 2 pi. So if I now want to find what x is, I simply subtract pi over 3. So 0 minus pi over 3 gives me negative pi over 3, which means that the starting point is going to be negative pi over 3. But now if I subtract pi over 3 from 2 pi, or rather 6 pi over 3 minus pi over 3, then I get an answer of 5 pi over 3. So that's our final result. 5 pi over 3 is going to be where this particular period ends. Which now should make sense, because if I were to add pi over 3 again, I'd get back to 0 and 2 pi. So now I should see as well that the coefficient of cosine is 1. And so I know that this amplitude is going to be 1. So it's going to rise 1 unit and fall 1 unit from the midline. But I also want to just demonstrate or show you why I don't draw my y-axis yet. The reason is because I want to fill in the y-axis based on where it's supposed to be once I fill in all of these x coordinates. It's possible that the y-axis is supposed to be right here because this is a negative and this is a positive. But if this was also a positive, now I'd know that the x-axis or the y-axis would have to be over here. And so we're going to fill in these important x values first. So let's go ahead and start going through the process. We're going to add them and divide by 2. So negative pi over 3 plus 5 pi over 3 is 4 pi over 3. 4 pi over 3 cut in half is 2 pi over 3. So I know that this midpoint is 2 pi over 3. Let's do that again. So let's add these together. So negative pi over 3 plus 2 pi over 3 is pi over 3. Pi over 3 cut in half is pi over 6. Let's do the same thing over here. 2 pi over 3 plus 5 pi over 3 is 7 pi over 3. 7 pi over 3 divided by 2 is 7 pi over 6. So if you've forgotten how to do something like that, let's just take a look at the algebra here. We have 2 pi over 3 plus 5 pi over 3 divided by 2, which is 7 pi over 3 divided by 2. But when I'm dividing by 2, it's the same as multiplying by 1/2, so I'm really just multiplying the denominators, which gives me 7 pi over 6. So now that I see all of the 5 important points that are 5 of the most important x values that are going to give me some answer, I'm now ready to draw my y-axis, which is somewhere between negative pi over 3 and pi over 6. And there's my y-axis. So now I'm ready to find out what the graph is going to look like. I know that in general, the shape of this graph will start at the top, drop down, and come back up again. But keep in mind that this minus 1 is causing me to move down 1. So now we got to think before we start here that if this is 1 and this is negative 1, and I move everything down 1, then that means the point that used to start up at the top at negative pi over 3, 1, and it would typically end here. Halfway in between, I would reach my minimum. Halfway in between, I would reach my 0. And halfway in between here, I would reach my 0. But notice that now, because of that movement of down 1, every one of these points is going to move down 1. So this point, the top left, is going to move down to the x-axis. This point that used to be a 0 is now going to move down to negative 1. This point that used to be at 0 is now moving down to negative 1 as well. This point that used to be at 1 is now moving down to 0. And the point that's at the minimum that used to be at negative 1 now has to move down to negative 2. So even though the amplitude is still 1, all we're showing here is that now every one of those original points had to shift down 1. Another way that I like to do this is to draw what that down 1 would represent. So this right here represents my original midline for this period. But if everything moves down 1, then that midline would have to move down 1. So sometimes I like to just draw this dotted line just to demonstrate that this is acting kind of like the new x-axis. And the reason why that's helpful is at the left side, this will now be 1 unit above the midline, and this will be one unit below the midline. So either way you choose to look at this process is fine. We're now ready to connect our dots, knowing that this is a cosine function and following that shape. And there you go. All right, so for one last example, we're going to put all of what we saw and all of what we learned together into one problem. There's all kinds of things happening to this. But the bottom line is that this is a sine function. So sine functions start at the origin, increase to pi over 2, decrease to pi, decrease to 3 pi over 2, and increase again back to 2 pi. Our job is to find all of those 5x values. In addition to this, we should also realize that because this has a -3, this is actually going to be flipped upside down and stretched out quite a bit. So it'll be stretched out. I know that's not symmetrical, it's not great, but that's what we should be recognizing here. And in addition to this, we should also see that this graph has moved up too. So let's just go ahead and start by finding our x values. And again, the way that I typically like to do this is by saying that if the original graph of sine x is normally between 0 and 2 pi, and I now see that the angle is not theta anymore, it's 2x minus 5 pi over 6, what we should recognize now is that 2x minus 5 pi over 6 is my theta. Okay, from 0 to 2 pi. And now we're going to solve for x in order to find out what the true period of this new function is going to be. So we can add 5 pi over 6 first. So that's going to give me 2x in the middle. If I add 5 pi over 6 to the left side, I get 5 pi over 6. And if I add 5 pi over 6 to 2 pi, keeping in mind that that's 12 pi over 6, and I add 5 pi over 6, then that means that the left side is 17 pi over 6. But I'm not quite done yet until I find what my x-coordinate is. So my x-coordinate, by dividing each of these by 2, just means that I increase the denominator. So that means the leftmost point of my first period is going to be 5 pi over 12, while the rightmost point is 17 pi over 12. And so I can go to my graph and plot 5 pi over 12 and 7 pi over 12. Now I'd like to just demonstrate something interesting about this, because this appears that the graph that used to start at 0, it would appear that this shifted right 5 pi over 6. The problem is it's starting at 5 pi over 12. Now where's the discrepancy? It seems as if it should have been at 5 pi over 6, but the algebra over here showed that it wasn't. So that's because when we end up wanting to find our transformation, we need to recognize that this function is actually the same thing as -3 sine of, and now if I factor out a 2 from both of those terms, the first term gives me x, and if I divide this by 2, I now get 5 pi over 12. So the only way that we could actually see the horizontal shift, if we choose to use that method, is by factoring out the coefficient of b, where we can now see that this actually shifted right 5 pi over 12. And not 5 pi over 6 like we may have expected. So we now need to just find some midpoints here. Okay, again, this should be 17 pi over 12. All right, so let's add these together. 5 pi over 12 plus 17 pi over 12. That gives me 22 pi over 12. Divide that by 2, and that gives me 22 pi over 24. But I can simplify by dividing numerator and denominator by 2, which gives me 11 pi over 12. Now that should make sense that 11 is halfway between 5 and 17. So now if I want to find the midpoint between 5 pi over 12 and 11 pi over 12, I add them together. 16 pi over 12 divided by 2 is 16 pi over 24. Both are divisible by 8, and so that gives me a midpoint of 2 pi over 3. And finally, lastly, if I combine these again, 11 pi over 12 plus 17 pi over 12 is going to be 28 pi over 12. Divided by 2 gives me 28 pi over 24. And both of those are divisible by 4, giving me 7 pi over 6. And so not all of the values on the x-axis are always going to have the same denominators because sometimes they can simplify. So if I were to take a look at this now, I should realize that the y-axis is going to be somewhere now over here. So if I now draw that y-axis, then that should show me where I'm at. Okay. Now, sometimes what you could do is you could just kind of put a little jagged line here to show that it's not drawn to scale, that even though this value right here is 0, that this distance may not equal this distance. And that'll happen sometimes. So now we would typically think, all right, well, this graph needs to go from -3 to +3. So normally 3 would be the highest point, and -3 would be the lowest point. Okay. However, this whole graph has moved up 2. So that means everywhere has to move up 2. So where the original midline used to be right on the x-axis, now the midline is going to be 2 units up above. So that's why we're going to look up here and see that if this is 2, even though this is not a horizontal asymptote, keep that in mind, it just bounces back and forth over this. But this is a good way to just kind of help to graph, because I now know that if that's my new midline, I have to go 3 units below that and 3 units above that. Okay. Another way to think about it is if the highest point used to be 3, now the highest point is 2 units higher, or 5. And if the lowest value used to be -3, the lowest value is now 2 units higher, or -1. So since this is sine, I normally would have started at the origin, but I'm not starting at the origin. I'm starting to the right, 5 pi over 12, but I'm also not starting there because I have to start up at the new midline since I moved up 2. So now it's just a matter of, again, filling in the beginning, the end, the halfway point, and now because of the fact that it is a negative sine function, the negative sine function causes me to start by going downwards. So that means this first one is going to end up at here, 5 pi over 12 and -1, I'm sorry, halfway in between is going to be right here at 2 pi over 3. And now at 7 pi over 6, I'm going to be 2 units or 3 units above 2 as well, which would put me up to 5. So again, if you think about the midline as just being this kind of dotted line that shows where you've moved to, then I should be able to move 3 units above, and I should move 3 units below. At the end, this is just a matter of connecting the dots. This right here, starting at 5 pi over 6, is still going to be the exact same shape as my original sine graph. The only difference is that because I've relabeled all of my x-axis, I can tell exactly where all 5 important points are going to be located. At this point, you could erase the dotted line just to demonstrate that you know that it's not part of the graph. It's not a horizontal asymptote. Okay. But I'm okay if you don't end up deleting that, but it is good practice just to get rid of that to show that, hey, it's not a horizontal asymptote, and there's our answer. So what you should notice is that even for trigonometric functions, the x-axis is describing the angles, the y-axis describes the corresponding outputs or ratios that we learned, but the transformations are exactly the same as any standard algebra function. Whether we're dealing with a quadratic or a cubic or a square root function, now we just have a couple new functions, sine x and cosine x, that are going to have these differing shapes.